Hi there, students. Welcome to class. Today's lesson comes from Chapter 1, Lesson 3, and is entitled Simplifying Square Roots. The two learning goals for the lesson today are to, first of all, learn to simplify square roots. So we'll be putting things in what's called simplest radical form. And secondly, we will be learning how to add, subtract, multiply, and divide square roots. So the first thing we're going to look at is what's called the product property for square roots. Now what the product property says is if A is greater than 0 and B is greater than 0, then the square root of A times B is equal to the square root of A times the square root of B. This is going to be a property that we're going to utilize as we try to break down square roots into what's called simplest radical form. And what it really means is you can break a square root down into its square root of its factors. For instance, if I wanted to find the square root of 200 in simplest radical form, what I could do is think about a perfect square factor. See if there is a perfect square factor of 200. And immediately I think of 100 because 100 is a perfect square. And it also is a factor of 200. And so what I do is I take that square root of 200 and I break it down into the square root of 100 times 2. And the reason why, again, I chose 100 because there's many different factors of 200. But first of all, 100 is a perfect square, and it happens to be the biggest perfect square that divides into 200 evenly. So once I have this 200 broken down into 100 times 2, then I can split up so that I have two separate square roots, and I have the square root of 100 and the square root of 2. Now the nice thing about the square root of 100 is it is a perfect square, and we can go ahead and take the square root of it to get 10. Now the square root of 2 is as simple as I can get without actually trying to approximate that as a decimal, and since I want exact values, the simplest radical form, then I can't really do anything more with that, and I just leave that as the square root of 2. So square root of 200 is actually equivalent to 10 times the square root of 2. This would be called simplest radical form, or SRF, simplest radical form. And in a way, it's kind of like reducing a fraction. So if you had something like 100 200ths, you wouldn't want to leave an answer like that. You would want to reduce it down to 1/2. And at the same time, you also wouldn't want to take a fraction like 100 200ths and reduce it to, say, 10 20ths. You always want to put it in its most reduced form, as low terms as you can possibly get. So here's another example. We have this where we might be using this property in the reverse. So if I had the product of the square root of 27 and the square root of 3, now neither one of those by themselves is a perfect square. But when I use this property in the reverse order, I can go ahead and multiply those and put them together under the same radical, and then go ahead and multiply 27 times 3, which gives me the square root of 81. And the great thing about this is that is a perfect square. So I can go ahead and take the square root of 81 and I get 9. You also want to keep in mind that really, technically, when we take the square root of 81, there's really a plus and a minus 9. There's just like over here with the 10 square root of 2, this was technically plus or minus 10 square root of 2, because every positive real number really has two square roots, a positive and a negative version. Okay, so before we take a look at any of these examples, I want to remind you of some of the most common perfect squares, your first few possible perfect squares. So for instance, we take 1 and we square it, we get 1. If we take 2 and we square it, we get 4. If we square 3, we get 9. 4 squared is 16, and so on. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared, 81. 10 squared is 100. And usually it's a good idea to, get to maybe the first 15 or 20 to kind of know them pretty much by heart. 11 squared is 121. 12 squared, probably one of the most common perfect squares, 144. 13 squared is 169. 14 squared is 196. And 15 squared is 225. And we'll stop there. But you could get, as many perfect squares as you possibly wanted by taking the integer values and just squaring them. And it is really a good idea to have committed at least this many, to memory. These perfect squares, 1, 4, 9, 16, 25, 36, 49, and so on. And when we talk about perfect square factors that we're trying to find, to factor out, this is basically a beginning of the list of those that we're talking about. So let's go ahead and take a look at this first example, number 1. It says to simplify each expression, and we have the square root of 20. So they kind of got it started for us. They identified the biggest perfect square that divides into 20 evenly, and that's 4. So I usually write that one first. So I rewrote this as the square root of 4 times 5. But now I can actually break those two factors apart and give them each their own radical. I could rewrite this as the square root of 4 times the square root of 5. And then I could just go ahead and take the square root of that 4 because it is a perfect square. And I get a plus or minus 2. Because it could be positive, it could be negative, and then there's nothing I can really do with that square root of 5. It's in its simplest form, and so that means that my simplest radical form of the square root of 20 is plus or minus 2 times the square root of 5. All right, let's try another one. So we have the square root of 63, and I started kind of looking through the list of perfect squares, and I came across a 9 that I know goes into 63. But I don't really want to stop at the first one I find that is a factor of that number. I want to see if maybe because I want to find the biggest perfect square. Otherwise, it would be kind of like equivalent to, taking that 100 200ths and only reducing it to 10 20ths. We want to be in as simplest form or lowest terms as we can possibly get. So we want the biggest perfect square that goes into 63. And it turns out that 9 actually is the biggest. But we want to maybe keep trying, and you might come across one that is larger that goes into it. In this case, 9 is the biggest. And so the 63 can be written as the product of 9 and 7. So it turns out that the square root of 63 is equal to the square root of 9 times 7, which means it's equal to the square root of 9 times the square root of 7. And the square root of 9 part is the perfect square part. So we're going to go ahead and take the square root of that. That's plus or minus 3. And there's nothing I can do more with that square root of 7. And so I just leave that as part of my answer. So it's plus or minus 3 times the square root of 7. So I'm going to go ahead and leave this one as a you try question. So I want you to go ahead and pause the video real quick and see if you can complete number 3. Okay, so plus or minus 4 square root of 5 would be equivalent in simplest radical form of the square root of 80. So let's take a look at that product property in reverse by looking at number 4 and number 7. So if you look at number 4, I have the square root of 3 times the square root of 12. Now neither one of those is a perfect square. Now I could take that square root of 12 and I could reduce it by taking out a perfect square factor. But one thing you might want to try before that is to see if maybe when you take the product of those two square roots, if you don't get a perfect square. And so I can use that property to work backwards and say, well, the square root of 3 times the square root of 12 is the same as the square root of 3 times 12, which then that turns out is the square root of 36, and now I know that's a perfect square. That's plus or minus 6. So it turned out by using that product property, I was able to actually get a perfect square that I could go ahead and give the integer square roots of. So go ahead and take a second and do number 7 as a you try question and tune back in to check to see how you did. Okay, so there you go. Plus or minus 12. Let's go back up and take a look at the quotient property. Now the quotient property says if A is greater than 0 and B is greater than 0, and by the way, the reason why we have to qualify the values of a and b is because, we can't take the square root of negative numbers, so we have to have positive values. So anyway, what it says is the square root of the quotient of a over b is equal to the square root of a divided by the square root of b. So that is like the product property in effect by saying that you can split the parts up. But in a quotient, our parts are our numerator and our denominator. And so if we have the square root of a quotient, we can rewrite that as the square root of the numerator divided by the square root of the denominator. Now here's an example of this, the square root of 25/49. Now if I tried to square root 25/49, I mean that number is, that's a fraction. It's not even a fraction I can reduce. But notice that both the numerator and denominator separately are perfect squares. And so by splitting them up and giving them their own radical sign, I'm able to then go ahead and take the square root of the numerator, which is the square root of 25, that's 5, and the square root of the denominator, which would be 7, and I get 5/7. But remember, that's also a negative 5/7 could also be a possibility as well. And that same property can be used in the reverse. So if I had something like the square root of 108 divided by the square root of 3, again, separately, neither one of those are perfect squares. But this time, if we use the property in reverse and rewrote it as the square root of the quotient, now if I take 108 and divide it by 3, I actually get 36. And then that leaves me with a perfect square to take the square root of. And the square root of 36 is 6, or also negative 6. So we have a couple examples down here that we're going to work together, and then I'll leave you a couple to do on your own. We're going to look at 5 and 6 together. So the square root of 64/25. Well, that's the same as saying the square root of 64 divided by the square root of 25. And the square root of 64 is plus or minus 8, and the square root of 25 is 5. So that's plus or minus 8/5. Now with the square root of 200 and the square root of 8, if I wanted to look at those separately, I could think about getting simplest radical form for the square root of 200, and I could look at finding the simplest radical form of the square root of 8, because neither one of those is perfect squares. But it turns out that if instead I think about this as a quotient of the square root of 200 divided by 8, I actually get the square root of 25. Because the square root of 25 then is an integer value, and 200 divided by 8 is 25. So that's the square root of 25, which is plus or minus 5. And I'd like you to try 8 and 9 as you try questions. So if you'll pause the video now, give those a try, and tune back in to check your answers. Okay, so go ahead and check your answers on those two. And let's turn the page. Okay, so what about if you have a fraction and its denominator is a square root? So if a fraction has a denominator that is a square root, you can simplify by what's called rationalizing the denominator. Now, rationalizing the denominator is where you find a way to remove the radical from a denominator. Now, a denominator, for whatever reason, whoever was originally the first person to decide this, decided that a radical in a denominator was not okay. You could have a radical in the numerator, but you couldn't have one in the denominator. Just like, I guess, at some point, somewhere way back, we decided that it was really not okay to have decimals in fractions. And so there's this process of what's called rationalizing the denominator, is where we're going to be multiplying the numerator and denominator by something that will actually take the radical out of the denominator. Now, the second thing that we're going to be looking at on this page is what we mean by like radical terms and how we can add, subtract, and multiply radicals. So like radical terms are square roots that have the same radicand, which means the same number under the radical, and they can be combined by adding or subtracting their coefficients. So that's how we can add and subtract radical terms. Okay, so let's take a look first at rationalizing the denominator. So rationalizing the denominator is to eliminate radicals from the denominator. So if I had something like 3 square root of 5 divided by the square root of 2, and doing that thing where we might, take the radical of the whole quotient doesn't work, what we can do is get rid of that radical in the denominator by multiplying that radical by itself. And so in the case of this particular problem, the square root of 2 is the radical that's on the denominator. And so we could simply multiply the top and the bottom of that fraction by the square root of 2, which really is just the same as multiplying it by 1, because anytime you have something divided by itself, that's just 1. And then in effect what that's going to do is square the denominator, because we're multiplying the square root of 2 by itself. And when we square a square root, that cancels it out. So what we're really doing here on the bottom is we're multiplying the square root of 2 times the square root of 2, which turns out to be the square root of 4, and that's 2. And so that's the way that we get rid of the radical on the denominator. Now when we multiply it on the top, we have to go ahead and put these two, the square root of 5 and the square root of 2 together, and that makes the square root of 10. So our simplified radical then would be 3 square root of 10 over 2. Let's go ahead and take a look at a few examples of that. So in number 10, we're asked to simplify by rationalizing the denominator, and we have 4 being divided by the square root of 5. So as you can see here, as they kind of helped us along a little bit, they went ahead and multiplied the numerator and denominator by the square root of 5. That turns the numerator into 4 square root of 5. It turns the denominator into the square root of 25, which we know that it's a perfect square, and so we can go ahead and take the square root of that 25, which is 5, and now it gives us our simplified radical of 4 square root of 5 divided by 5. Now if there was anything more I could reduce, like if the numerator and the denominator could reduce any further, I'd have to go from there, but this is as low as it goes. And because we're dealing with square roots here, I just want to keep in mind the fact that first of all, the things we're taking the square roots of have to be positive, and there's always the potential that you have that positive and negative version. So let's take a look at the next example. We have 1 divided by the square root of 6. Okay, so what that means is I've got to get rid of that square root of 6 that's in the denominator, and so I'm going to multiply both the numerator and the denominator by the square root of 6. That's going to turn the bottom into the square root of 36. It's going to turn the top into the square root, or 1 times the square root of 6. Now the square root of 36 is 6, so that's really the square root of 6 over 6, which cannot be reduced any further. Okay, so in number 12, we have 3 times the square root of 2 divided by the square root of 8. Now, having a radical in the numerator is fine, so we really don't care about that square root of 2 that's in the numerator. That's okay. The one that we care about is the radical that's in the denominator, because the rule is you just can't have a radical in the denominator. And so what we want to do is actually multiply both the top and the bottom by a square root of 8, because that's going to turn the denominator into the square root of 64, which actually is a perfect square. Now we don't even actually really technically have to show this step to it, because the square root of 8 times the square root of 8 would automatically give us 8, because we're squaring basically the square root of 8, and that cancels out the radical. Now on the numerator, we have 3 times the square root of 2 times the square root of 8. Well, the product property says the square root of 2 times the square root of 8 is the same as the square root of 16. Well, it turns out this time that square root of 16 is a perfect square, and when I take that square root, I get 4. So my numerator is really 3 times 4 divided by 8, and so this is really the same as 12 eighths. And I can then reduce that down to 3 halves. So my final answer is 3 halves. Well, that's definitely much simpler than the original. Okay, so on to our final learning goal, to add or subtract like radicals. So when we add or subtract radicals, it's kind of like adding or subtracting with variables. So say for instance, something similar to question number 13, instead of saying 12 square root of 7 minus 4 square root of 7, let's say it said 12x minus 4x. So when we have variables that are the same, have the same variables and raised to the same powers, we call them like terms. So when we add like terms with variables, we just simply add or subtract the coefficients. So that's what I would do here. 12x minus 4x is 8x. So you can kind of think of a like radical in the same way that you think of variables. So subtracting 4 square root of 7 from 12 square root of 7 is just like subtracting 4x from 12x. But instead of getting 8x, we get 8 square root of 7. Now, question number 14 combines some of the things that we've been doing in this lesson, the first of which is simplified radical form. So on the first part of number 14, the square root of 75, if I wanted to simplify that, put it in simplest radical form, and because right now I can't really do anything with these radicals because they're not like radicals, but if I break the square root of 75 down by taking out the perfect square factor of 25, it turns out that this is 5 square root of 3. If I do that same thing with the 27, that turns out to be, because it's the square root of 9 times the square root of 3, that turns out to be 3 square root of 3. Now those are like radicals, and if I subtracted 3 square root of 3 from 5 square root of 3, I get 2 square root of 3. And that's my final answer there. So I'd like you to try number 15 as a you try question. So pause the video now and tune back in once you have an answer. Okay, so once you finally simplified the square root of 45 down to 3 square root of 5, you could see that these were like radicals, and we went ahead and added them together by adding the coefficients to get 9 square root of 5 for our final answer. And that does it for our lesson today, so I'll see you in class.